I'm Jonathan Leake, and I'm going to be talking about capacity bounds via productization, and this is joint work with Leonie Gervitz. Okay, so here's the outline of my talk today. First, I'm going to give a little bit of background on the main result. It's a little bit technical, so I'll kind of give some background on what it's saying, then I'll give the main result, and then from there I'll discuss the kind of two main applications that we talk about in our paper. Give a few details of the proof, and then discuss some open questions at the end. Okay, so here's the first section. So the first thing I'll do is define for you polynomial capacity. So you start off with some polynomial in n variables that has non-negative coefficients, and capacity is then defined as follows. So it's just this infimum over the strict positive orthant of the evaluation of the polynomial divided by the product of the inputs. And this one that's here in the subscript is there because sometimes you can exchange that out for different vectors here, and then that changes the denominator exponent. But for this whole talk, we'll mainly be working with just the all ones vector there. Okay, and this may look kind of like a strange kind of starting point. When I first saw this, I didn't have very much intuition for what was going on. And I won't be able to give you a lot of intuition for it, but I will give you some examples of applications that the capacity has been used for. So it's mainly used to give bounds or approximations for certain, usually combinatorial quantities. And some examples are the permanent and mixed discriminant. Those were kind of the original examples that capacity were used for. There's also a number of examples where counting or approximating the number of contingency tables, which are the integer points of a particular polytope, a transportation polytope. You also have some things related to graphs. So you have you can count Eulerian orientations of a graph. You can count k-matchings of a bipartite graph. You can also do some counting and optimization problems on certain classes of matroids, and also counting the intersection of two matroids. And also, last, there are connections of capacity to this idea of matrix or operator scaling, which are certain algorithms for kind of converting a matrix into having certain row and column sums. And also, this kind of idea also has a much more general branch into invariant theory, and there are a number of authors that have worked in that direction. Okay, so this is capacity. These are kind of the things it can be used for. And the other main thing that we're going to need is kind of the polynomial classes that capacity is usually used with. And for the most part, pretty much all the applications I mentioned on the previous slide, the types of polynomials that are used are either what are called real stable polynomials, or more generally, certain classes of log concave polynomials. And before I define real stable or log concave here, I need to make a connection between real stable polynomials and what are called there in the title strong Rayleigh distributions. So the first thing I'm going to say here is just a more general connection that one can make between polynomials and distributions. And it's a very simple idea. You take a polynomial that has non-negative coefficients such that when you plug in the all ones vector, you get 1. And what this is going to mean is that if you expand the polynomial in terms of its coefficients and its terms, it means that the coefficients are all going to sum up to 1. That's exactly what this condition means. And so what you can do is then construct a discrete distribution on the support of the polynomial by basically saying that here's a discrete distribution mu. The probability that mu is equal to kappa, one particular degree vector showing up in the polynomial, is just equal to the coefficient. Okay, and one of the nice things, and one of the things we'll utilize the most about this connection between probability distributions and polynomials is the idea that, okay, so this mu is a random vector. It's a random degree vector. And if you consider its entry-wise expectation, you get what I'm going to refer to as the marginals or the marginal probabilities. And the reason they're called that is because if you assume further that actually your degree vectors are all 0, 1 vectors, you can think of this mu as being like a random subset of the set of variables. And then these are literally marginal probabilities where they give you, what's the probability that the ith element is in your set. But I'm going to use this kind of notation more generally as well. And the nice thing here is there's this really nice connection between this thing that has this conceptual meaning and this other thing here, which is something that maybe has some analytic meaning on the polynomial side. But it's the gradient of the polynomial at the all ones vector. Okay, so this is going to be something that you want to keep in mind. Okay, so let's get back to these real stable polynomials then. So okay, we have this connection between the polynomials and the distributions. And now I'm going to define real stable polynomial to be a polynomial with real coefficients, such that whenever you plug in all entries in the upper half plane, you never get 0. Okay. And the connection to some distribution, these strong Rayleigh distributions, is maybe you could call this a definition. I'm just going to define a strong Rayleigh distribution to be one that arises in this way from a real stable polynomial. So these are sort of identified definitionally. Okay, and so we have these real stable polynomials, strong Rayleigh distributions. So what are these? Why can we say that real stable polynomials are log concave? What is their connection to log concavity? The most basic thing, which if you've seen this before, this is a pretty standard thing. If you take a real stable polynomial that just has one variable, just say x1, then this is basically saying that you have a polynomial with real coefficients with no roots in the upper half plane. But since this is real coefficients, it means it also has no roots in the lower half plane because they come in conjugate pairs. And so in fact, all your roots have to be real. And there is a very old result called the Newton's inequalities that say that basically a coefficient sequence of a real-rooted polynomial has a certain log concavity property. So this is like maybe the first way that you might see log concavity in these polynomials. But of course, we want to be able to handle multivariate things. And for multivariate polynomials, you have something much kind of stronger called, or not really called, but what you might call negative correlation for the marginals. So this basically says that if one of the marginals gets large, then kind of the probability that other marginals are large also gets smaller. So the marginals are sort of negatively correlated. And you can think of this as kind of a concavity type statement, because for positive correlations, you think of it as more of a convexity type statement. And so this is, there's, you can really get into this, and there's a lot of very interesting things here that I won't have time to talk about, but this is like you should think of this as a log concavity type statement. And some examples of these distributions or these polynomials are the uniform distribution on spanning trees of a graph, determinantal point processes, and also there are many more examples here. And if you're interested in this type of thing, there are this Borsea, Brendan, Liggett paper is quite good, and there are many other papers that you can take a look at. And just as a last point, there is actually a more recent generalization of this class of polynomials. They have a number of names that all three of these turn out to be equivalent. Gervit's generalization was actually a little bit longer ago, 10 years ago, but these two other names were much more recent, and they have had a lot of applications recently. So this is kind of this is a nice generalization, but we're gonna mainly stay focused on real stable polynomials. Okay. So with this, now we have this notion of capacity, we have real stable polynomials and their associated distributions. Now we can give the main result. So we start off with polynomials P, non-negative coefficients, such that you plug in the all ones vector, you get 1. We know that this gradient turns out to be the marginals, and here is the main result. So we start with some P that is homogeneous and has some nice properties. If we assume that P is real stable, and that the marginals, right, what is this saying? The marginals are close to the all ones vector. So the difference in norm is less than 2. Then we get this bound on the capacity. This bound is sort of easy to get. This is the main bound here. And the way that you can interpret this is to say, okay, well, when the marginals are near the all ones vector, then the capacity is near 1. But this is sort of like a quantitative statement. I mean, this first part kind of conceptually is sort of straightforward if you think about things for a little bit, but the quantitative features of this are really the kind of the content of this result. And if you use a previous result of Gervit's, you can also get something kind of immediately from this, which says that this coefficient, this is the all ones coefficient of P, is bounded below by this quantity, which if you then translate this into probabilistic terms, this is saying that you can get a bound on the probability that your distribution equals the all ones vector based on the closeness of the marginals to the all ones vector. So this is what you can get. Okay, so still kind of technical results. So let's just move right on to the applications. Okay, so the first one is towards this what I refer to as a matrix scaling bound. So the goal of matrix scaling is you start off with some matrix with non-negative entries, and you want to multiply on the left and right by a diagonal matrix with positive entries to make A doubly stochastic, which just means that the row sums and the column sums all to add to 1. So you want to somehow multiply on the left and right to get this property. Okay. And there's sort of a standard at this point algorithm called the Sinkhorn scaling algorithm that's used for this. And basically the idea is as follows. Well, I know by multiplying on the left, I can make the rows all one, like all sum to 1. Great. But of course that doesn't fix the columns. Okay. So once I've done that, let's do it on the columns now. Okay. So I can multiply on the right by some matrix and make the columns all sum to 1. But now I've sort of screwed up the rows. So let me go back and fix the rows again. Then I've screwed up the columns. Let me go fix the columns again. And it turns out if you keep doing this, and under some nice conditions of the matrix, this will converge. This process will converge to a doubly stochastic matrix in the end. And so from this was the exact algorithm then that was used by this group of linealists, Samorodnitsky and Victorson in 2000 to deterministically approximate the permanent of a matrix with non-negative entries within this factor. And how did they use this algorithm and the fact that it's converged? Well, okay, so the first thing was at each step, they're just multiplying by a diagonal matrix. It's easy to keep track of changes to the permanent. Okay, so that's great. Like at every step, we can keep track of how much the permanent has changed. And at the end, when the matrix is finally doubly stochastic, we have an approximation. This is this van der Waarden bound, which was proven in the 80s. And so we want to get the permanent of this starting matrix. We know how to track the changes and we know what it should be at the end. The only problem remaining is actually, you know, this is an algorithm. I mean, you're not going to actually converge to something doubly stochastic. You're just going to get close. And so somehow you have to be able to get a version of this bound that works for things close to doubly stochastic. Okay, and you can maybe see how this would relate to the main result of the previous slide, because this is saying if the marginals are close, then you get some kind of bound. This is exactly the sort of thing we want. And they were able to get some bound. But let's see how our stuff applies. So here's how it works. What polynomial did we use? Well, there's a very interesting polynomial related to the permanent of a matrix. If you've never seen this before, I would recommend trying to work this out. It's a pretty interesting thing. You take this polynomial, which you have your matrix, and for every row, you create a linear form out of that row by just dotting with a vector of variables. You then product together all those linear forms. This is very easy to see that this is a real stable polynomial. And it turns out that the all ones coefficient is exactly the permanent of the matrix A. And if we enforce the row sums to be 1, that's going to give us this condition, which we need. And if we do this, what that means is that the column sums of the matrix are going to exactly be the marginals. So this has all the pieces we need, so we can apply the theorem. So what does the theorem say? Well, the theorem is stated in terms of the 1 norm here, but I've sort of given the equivalent thing in terms of the 2 norm, just using the standard inequality. It says this inequality here. It says that the permanent, right, this all ones coefficient, is bounded below by this quantity. And if you exchange this out for the 2 norm using the standard thing, we actually improve upon the bound of the previous slide. And in fact, this gives a tight improvement over the bound that they got. Okay. And also this type of thing, this type of inequality and this type of idea is used for these more recent operator and tensor scaling algorithms. But more generally, this type of idea is, we hope that we can use this kind of generalization of their bound to real stable polynomials in general to attack other types of kind of approximation algorithms, like the analysis of approximation algorithms that use similar types of kind of scaling techniques. But currently, this is our main kind of application in that direction that we can improve upon and kind of give a kind of a cleaner kind of discussion of this kind of bound that they have for this scaling algorithm analysis. Okay. So the other main application we give is related to this very recent exciting work on metric TSP. So TSP is the traveling salesperson problem, where metric means you just assume the triangle inequality. So this is a hard problem, even approximation within a particular factor. But there is an approximation that one can do efficiently within a factor of 3/2. This is kind of from the 70s. And very recently, I put 20 here, but of course, you could also put 21. This Carlin Klein Ovescaron paper is in STOC this year. This factor was improved very slightly below 3/2. And the main tweak here is a random spanning tree is used based on some linear relaxation. And if you remember, right, spanning tree distributions have this strong Rayleigh property. So we expect some kind of connection here. And that, I mean, that's how we make this connection. Or I mean, they made the connection, honestly. But anyway, we'll talk about that on the next slide. Okay. So the thing is that this obviously is a well-studied problem, and there have been a lot of improvements for many special cases, but there's never been a general improvement until this paper. So this is obviously a big deal paper. And now I'm going to kind of just like ignore all of the stuff that they did, except for the stuff that's connected to our paper, and I'm just going to talk about how our paper kind of connects to theirs. Of course, if you want to know more about what's going on in their paper, you should definitely check out their talk. Okay, so let's see how this relates to R bound. Okay, so this is how it goes. So now we're going to have some new, which is some strong Rayleigh distribution, where now your degree vectors are all 0, 1. And what that corresponds to is picking a random subset of 1 through m. And we're going to construct another distribution, basically by you kind of partitioning 1 through m into a bunch of sets and kind of summing all of kind of the marginals within those sets. So this makes some new distribution, which I've denoted by these capital AI, and it turns out this process preserves the property of being strong Rayleigh. So this AI gives us another strong Rayleigh distribution. Okay, and there's a kind of a line from their paper, which now I'll quote, which basically says that roughly speaking, they show that one of the technical pieces that they need is that they show that whenever the expectation of this A is close to all ones, where it's bounded above by this, it means that the probability that A equals the all ones vector is bounded below by some function which is doubly exponential. Okay, and they make some comment about how, okay, if we can improve this doubly exponential to singly exponential, then we can make improvements on this approximation constant. Okay, and so if you then take what we do and apply it to this kind of a polynomial associated to this strong Rayleigh distribution A, right? It's strong Rayleigh, so P is real stable. And our bound says, if you kind of apply it to this situation, you get that if the marginals are close to the all ones vector, then this coefficient, which is exactly this thing, is bounded below by this. And so this immediately looks a lot better than this doubly exponential, right? We have this epsilon to the d instead of this epsilon to the 2 to the n. And so that looks really good, but unfortunately, it's a little bit deceiving because this d can be dependent upon m, and it is crucial to their analysis that it's not dependent upon it. So this doesn't immediately apply to their situation, which is unfortunate. But we sort of hope that it will. We sort of think and hope that it will, because somehow the result that we have in our context is tight in some way, and so we expect these techniques, if we kind of, instead of doing things in our context and trying to transfer it, if instead we try to transfer the techniques to their context, we sort of hope that things will that this can be fixed and that actually the improvement can be made using these techniques, but it's unclear. Okay, so those are the main two kind of applications that we have for this bound. Okay, and let's just very briefly talk about the proof for a minute here. So the proof comes in two parts, and I will, there's one kind of main concept here that called a product polynomial. That this is where the term productization comes from. And so let's talk about this, and I'll give you the two pieces. So product polynomial is just one that looks like this polynomial we associated to a matrix. You have some matrix with non-negative entries, and to each row, like we did before, you take each row and you dot it with a vector of variables to get these linear forms here, and then you product all those linear forms together. Okay, and this is a real stable polynomial, but it's much more specific than that. It's sort of like a matrix polynomial somehow, or a polynomial associated to a matrix. And what we do is we say, okay, when the row sums are all 1, and when the column sums are some vector alpha, we say that this polynomial lies in this class. Okay, and then the proof comes in two parts. So the first part is we prove our bound for product polynomials. So that's basically what this says. If our alpha, which we're going to call these the marginals, if you remember, this was equal to the gradient of p at the all 1. So if the marginals are close to 1, then that means that the minimum possible capacity you can get is bounded below by this. So this gives you a lower bound on the capacity. Okay, so that proves it for these product polynomials. And then how do we sort of take the product polynomial bound to real stable polynomials? Well, it's with this result. So if we have P being real stable, homogeneous with marginals alpha, then for any x in the positive orthant, we can find a product polynomial with the same marginals such that they are equal at this one point. And this may seem like kind of a not a hard thing to prove. You just have to show that two things are equal at the same at a single point. But it turns out actually this is non-trivial. And if you think about this, right, we have a min here and we have an inf in this capacity. And so by basically swapping the inf and min, you can kind of sort of take the inf over all x greater than 0 here of this, and it basically immediately gives you the bound for real stable polynomials. So this is exactly what you need to transfer this bound to real stable polynomials. Okay. So let's talk very, very briefly about the proof. The first part is the bound for product polynomials. And essentially it follows from this lemma, which is sort of like, well, it's a pretty interesting fact. It basically says that this condition on the marginals, being close to all ones, is equivalent to saying that every matrix within this space has permanent greater than 0. So this is a condition on the column sums of matrices that enforces the permanent to be greater than 0, regardless of anything else you know about the matrix. And it turns out this is also equivalent to some kind of, sort of Hall marriage type condition. I won't say anything more than that, but that's sort of what sort of thing this is. Okay, and I'm not going to talk too much of the proof. I'll kind of put it up there in case, you're watching the video and you want to pause and take a look at it. But roughly speaking, you sort of kind of get some kind of extremal matrix. The fact that it's extremal means the permanent has to be 0, and then you can kind of rearrange what that means to get some kind of bound on the capacity. So that's about all I'll say there. But these are kind of the big points of the proof. Like I said, I'll just put it up here in case you want to take a look. The second part then is this productization. So how do we have some, we know that we have the bound for product polynomials. We want to sort of take our real stable polynomial and link it up with this product polynomial so that we can transfer the bound to real stable. And the key lemma there is due to Brandon, which basically says in the case that the marginals are the all ones vector, so this specific case, we have this kind of majorization result where you take an x and then you look at the roots of the linear restriction through that x and you get this majorization relation. And if you know what majorization means, it basically says that you have some doubly stochastic matrix, and a doubly stochastic matrix is a matrix where the row sums and the column sums are all 1, and that's exactly the matrix that you use for this product polynomial. So from this kind of as an immediate corollary, well, almost immediate corollary, you get the result for marginals equal to 1. To then generalize it to other marginals, you kind of do this trick where you start with rational marginals. You kind of blow up the polynomial p to make this q that has a lot more variables and a lot higher degree. And q now has the property that its marginals are 1. So you sort of kind of I don't know, like disseminated the marginals among a bunch of variables. And then this lemma immediately gives you this product polynomial that satisfies the theorem. And then the point is, right, once you have that, you can sort of then sum up blocks and that you end up getting the result then for these rational alpha. And for irrational alpha, you can use this technique I've written here. There's also some perturbation argument. To go from rational to irrational is not that bad. Once you have rational, you kind of have it. Okay, so those are the highlights of the proof. And finally, let me just talk about some open questions. So the big open question is, can we actually use this to improve the metric TSP bound? Right now we cannot, but we kind of hope that we can. The other thing is, right, we've proven this for real stable polynomials. Can we prove it for log concave polynomials or strongly log concave polynomials? Unclear, right? The productization result required knowing something about the roots of polynomials. We don't have roots in this case, so we would need some new techniques. And last, are there other applications, right? We had this bound for matrix scaling, which that's a very well studied problem. But are there similar quantities that one can bound using the same type of techniques? And that's it.